Welcome to Masters for Operation 2 course. Today I will start discussing on this liquid extraction. The syllabus is as follows: introduction to liquid extraction, liquid equilibria, then effect of temperature on liquid equilibria, design calculation of single stage extraction, design calculation of multi stage extraction, and finally selection of the extractors. Now we will be discussing on introduction to liquid extraction, followed by this liquid equilibria. So, in the beginning we need to understand the process liquid extraction, that is liquid extraction. Sometimes it is designated as LLX. It is a mass transfer operation in which a solution containing this feed, that is a mixture of solute and carrier solid, is brought into intimate contact with a second immiscible or slightly miscible liquid in order to achieve the transfer of the solute or solutes from the feed to the extracting solvent. The solute rich phase is called extract, and the residual liquid that may have the little of the solute left in it is called raffinate. So, if we say this one schematically, say the feed is of these dots, and with the we can say the carrier solvent, it is initially there in the beaker, and then second liquid actually is fed inside this beaker, and it is mixed properly to get this suppose homogeneous mixture, and it is allowed for a long period of time, so that the two liquids will be separated from each other due to this density difference, and the solute or this we can say this target component, that is the dot, now is distributed like this. It is maximum amount of the dot has gone to this extracting solvent, and minimum amount of the solutes are present in the carrier solvent, and if it is allowed for a long period of time, then it will be separated into two different liquid phases. This one is that we can say this one rich in the solute, that is we can say this an extract phase, and the raffinate means the exhaust phase, where the we can say this small amount of the solute will be present. Now, this extraction mechanism, this is very simple mechanism, that firstly we need to bring the feed and the extracting solvent into the intimate contact by dispensing one phase into the other as the droplets. Suppose in the beginning we have the feed with the solute and the carrier solvent, and then we will be adding this extracting solvent into this feed, and then we have to mix this properly, so that it will be dispersed as the droplets. Now, depending on the miscibility of the target component, that is solute in the extracting solvent, say these two will be separated into the two different, say the solute will be moving from this carrier solvent to the extracting solvent. So, now we can say the second step will be separation of the extract and the raffinate phases. So, it is dependent on the density difference between the two solvents. Now, we need to do the third step, is that a most important step, that is removal and recovery of the solute from the extract phase in a relatively pure form, and the fourth one, that is we can say this one the residual part, that is removal and recovery of the solvent from the say from each phases, like this we can say this one from the extract phase as well as this raffinate phase. So, by distillation usually, but there are so many other ways also. Now, if we talk about the economics of the extraction process, then it is very interesting also. In a typical liquid extraction process, only about 15% of the capital cost goes towards the extractor, and the remaining 85% goes towards the distillation, or we can say this on other equipment of the solvent recovery and product purification. And in terms of we can say this on cost, only 5% of the operating cost actually is required for extractor, and remaining 95% towards the solvent recovery. So, we can say from the economic point of view, the extraction is not stand-alone process, but it is dependent on other separation process. But if there is no other alternative, other than extraction, we need to go for that. So, we will be discussing this one, like where the extraction favors our distillation process. So, there are so many, but here we are giving some examples like this. The components to be separated have these close boiling points. So, then distillation, using distillation we cannot be separating these two components. If the relative volatilities also are close to unity, then number of trays in the distillation column will be very large, and then extraction will favor over this distillation process. Sometimes we can say this one heat sensitive material to be separated, like antibiotics, vitamins, etc., using this extraction process, then we can say this one distillation process. Sometimes recovery of non-volatile solutes, usually from aqueous solutions in hydrometallurgy, that is done by extraction process. And suppose for a very dilute solution, there we cannot separate using this distillation process or any other processes, but there extraction process can efficiently separate the target components from the dilute solution. And some removal of the organics from the aqueous streams, like phenols from aqueous wastes, are done by extraction process, where that cannot be separated by distillation process. So, few examples of the solvent extraction process we will be discussing here, then we will be going into the details of the extraction process. Like this, first example is extraction of aromatics in petrochemical industry, like this benzene, toluene, xylene, these are separated from petroleum fraction by furfural, sulfonal or NMP, diethylene glycol or methyl ethyl ketone or methyl isobutyl ketone, etc. These are our extracting solvents. And say recovery and concentration of antibiotics, like we can say penicillin, it is only recovered using this extraction process other than other masters for operations. Like the penicillin is produced by fermentation, we know this one, from the fermentation broth, we can separate this penicillin using this extraction process. The concentration of the penicillin in the fermentation broth ranges from 20 to 30 gram per liter, and the recovery and concentration of penicillin actually is done usually using a solvent such as say amyl acetate or butyl acetate or methyl isobutyl ketone. So, we can get this one very schematically, we can explain this one very easily, like this. We have this fermentation broth like this, around pH 2, it is extracted using in the water. So, we can say this at around pH 2, penicillin remains in the acid form and has a low solubility in water, but it is extracted in this system. But once we will be increasing the pH up to 7.5, so but it favorably transported to the organic solvent from the aqueous fermentation broth because of the high distribution of the coefficient. So, whenever we will be adding some amount of the solvent here, and then say we can say this one, due to this high distribution coefficient, it will be going to this organic solvent. Then this one pH is maintained at around say 7.5. So, in that pH, say this pH actually dependent distribution of penicillin in the water ester pair is made use of to recover, purify and the concentrate from the broth. Total experiment actually is carried out at 40 degrees Celsius. So, at pH 7.5, it is, we can say this one, the penicillin actually comes to the aqueous extract, and whatever the solvent actually is used here to extract, it is now almost free from the penicillin, it is recycled back to the system. So, this way we can say this one the extract, and we can say this one from the extract, after separating the target component, the whatever the extracting solvent is again reused for the same extraction process for so many cycles. Now, the another example is the extraction of caprolactam, that is we can say this used to manufacture this nylon 6. So, it is synthesized from the cyclohexane, we know this one, we are not going to the details of the process, but we will be discussing the one step where the we can say this one, we can use the extraction process to separate a particular target component like this cyclohexanone oxime. Like this we can start with the cyclohexane, then from the cyclohexane to cyclohexanol, then it is to cyclohexanone, then the step is cyclohexanone oxime, and then from the cyclohexanone oxime to caprolactam. So, in this step we can see this is the last step of the process involves the reaction of the oxime with sulfuric acid to get the caprolactam and forms this caprolactam and ammonium sulphate. So, the reaction mixture separates into an organic rich phase where we can say this one caprolactam is there, that is called lactam oil, that contains 65 to 70% caprolactam. These two phases are fed at the appropriate locations of a rotating disc contactor, that is we can say the one extracting unit, that toluene is used as the extracting solvent. Then caprolactam goes to the extract means in the toluene phase, and ammonium sulphate actually remains in the raffinate or we can say in the organic or aqueous phase. These two streams are further treated to get the caprolactam in a pure form and to recover the solvent and ammonium sulphate. So, all these will be again used for different purposes, and the other few other applications are like in food industries and pharmaceuticals, in metallurgical and say environmental and organic and inorganic industry. So, there are so many applications of the extraction process. We will be discussing the details of the extraction process now. So, before that actually we need to understand the equilibria, that is liquid equilibria, and now also we will be learning about the ternary diagram to understand the liquid equilibria. Suppose our liquid extraction system contains at least 3 components like this. One will be the solute, that is we can say this target component. So, we will take this as solute C, and carrier liquid actually in the feed, that is we can say this one when we have this feed C is dissolved in A, and we are adding this extracting solvent from the outside. So, this is we can say this one B. For the entire extraction calculation as well as this whenever we will be discussing about the leaching process, that is a solid liquid extraction, there also we will be using these notations like solute as C, carrier liquid as A and extracting solvent as B. So, now we need to understand the classification of the ternary system. Suppose now we have this A, this we can say carrier solvent, B is the extracting solvent and C is the solute. So, out of these 3 components we have 2 binary systems like this, 3 binary systems AB, BC and CA. So, mutual miscibility behavior of the component determines the nature of the equilibrium diagram. So, what type of equilibrium diagram actually will be there, that will be determined by the mutual miscibility of A, B and C. Like say the first system is like this, we can say this one solvent and extracting solvent. So, carrier solvent and extracting solvent are practically immiscible. So, that is we can say this one, that is one system, say we can say it is of no use. In general we can say this one in the liquid extraction system. If solute is not, we can say this one miscible, this one carrier solvent and extracting solvent are practically immiscible. So, that is we can say this one, these two are not miscible to each other, but we can say this one solute C can be miscible with both A and B. And the second type is called, we can say this one, the solute is miscible with carrier solvent and extracting solvent in all proportions, that is we can say this one type 1. This is the we can say this one very good type of the we can say this one ternary system, where we can say this one both carrier solvent and extracting solvent have the miscibility of target component in all proportions. And the last category like this, we can see this one solute C is completely miscible with carrier solvent, where the feed is, but both solute and we can say this carrier solvent have limited miscibility with the extracting solvent B. So, that is we can say this one type 2. So, we have this both type A1 and type 2. And based on their miscibility actually we will be discussing the liquid equilibrium curve. So, before that we need to understand that equilateral triangular coordinate, and we need to understand this very precisely, otherwise we will not be able to solve any extraction problem. Let us take a mixture of M like here. So, whenever we will be talking about say 100% A means this one, then say 0% A will be in this line. So, this is we can say 0% A. So, this is 20% A, then this is 40% A, this is 60% A, this line stands for 80% A and this tip is 100% A. So, we can say this for M we have this 20% A. So, we can say this one carrier liquid contains 20% A here. So, whenever we will be talking about this 100% B means say this one we can say this one 0% B, then 20% B, then we can say 40% B, this is 60% B and this is 80% B, this is 100%. So, this is we can say this one 20% B is there. So, this one whenever we will be talking about this 100% C. So, this is 0% C, this 20% B, then it is 40% B, this line 60% B, this is 80% B, this is 100%. This tip stands for 100% C. So, this line this one corresponds to 60% C. So, in all points C population is 60%. So, then we can say this one for M, A contribution of A is 20%, B is 40%, 20% and C is 60%. So, all these are actually in the liquid phase. So, all A, B, C all are in the liquid phase. So, we can say this one carrier liquid contribution is 20%, extracting solvent is 20% and this one solute is we can say this one 60%. And this convention will be used for the entire extraction study. Now, we will be discussing about this type 1 and type 2 where this we can say this one liquid equilibrium is. Say C is miscible with A and B in all proportions, we can say this one all proportions for any proportion. So, we can say this one A and say C will be miscible in all proportions. Like this we can say this curve, this we can start from R to P to S. So, in between this one we can say this one this is binary phase zone. So, here you see we will be discussing in detail about the binary phase or we can say this one two phase region where we can say this one from R to P. So, that is actually you can say A, this 100% A means this is we can say this one carrier solvent. So, carrier solvent rich zone. So, this is we can say this one raffinate arm. We learn this one that whenever the exhaust stream will be there where this less amount of the solute will be present. So, you see this solute also will be very less amount because 100% is here. So, definitely this less amount of the solute will be present in the carrier solvent and this B is actually we can say this one extracting solvent. So, B is extracting solvent. So, here from P to S that we can say this one raffinate arm, that is say extract arm. So, this one we can say this one from R to P this is raffinate arm, from P to S this is extract arm. Okay. So, this suppose for this two phase in this two phase equilibria line, so suppose from G1 and H1, suppose G1 and H1 this is connected with one tie line. So, these two liquid phases are in equilibria and from suppose from G2 to H2 that is also in the equilibrium. Suppose we have added this one extracting solvent in the feed and we have mixed this properly. Suppose this K is one particular point and we can say this one K is a particular we can say composition. If we wait for a while or we can say this one if we allow this entire system to be separated from each other, then it will be separated like this. With G2 composition it will be in the raffinate phase and H2 composition in the extract phase, and that is why G2 and H2 that is we can say this one tie line. So, G1 is rich in the carrier, we can say this one G1, G2 both are rich in the we can say this one raffinate and H1 is rich in the extracting we can say this one solvent that is called H1, H2, H3 all these are we can say this one extract and say G1 H1, G2 H2, G3 H3 all these are, we can say this one, these are all tie lines. And then one point is there, that is a common point, that is P, we say this one is the plate point. We will be discussing in detail about that. And then this point P, that is determines or demarcates the raffinate and the extract sides. I told that this one RP, this part you can say this one as this raffinate arm, and this is, we can say this one extract arm. So these two, so these raffinate and extract sides actually of the equilibrium curve, that is called, say P is called plate point. This type of curve actually, this RPS is called this binodal, because it has two arms like RP and PS. Okay. A liquid mixture having this overall composition corresponding to point K, suppose I told that, say this overall composition K is there, and we are waiting for a long period of time, so that these two will be separated into two different phases, liquid phases. One, we can say this one raffinate, and another this one extract. So this composition will be G2 will be the raffinate phase concentric composition, and H2 will be the extract phase composition. So keeping undisturbed, it separates into two phases at equilibrium. The compositions are, we can say this in G2 and H2. So this amount actually will be obtained by this lever rule, that is, we can say this one G2 divided by H2 equal to, say this one opposite arm, this KH2 by Kg2. So this is, we can say this one, using this lever rule we will be able to get the, what will be the composition of the extract arm and the raffinate arm, or we can say this in extract composition and raffinate composition, and it is actually controlled by this what is called the tie line. Okay. The another type, what is we told that this A, B and BC are partially miscible. So in that case there is no plate point. So this raffinate arm will be like this, and we can say this one extract arm will like this, and then tie lines, all the tie lines are this one obtained in this way. So this is one tie line, we can say this one in the, we can say this BC, the line where we can say the 100% C is present, and also in between this AB, this line, this is also one tie line. Okay. So here there is no plate point, but you see we will be also discussing this one, if we do something modification, here also we will be able to get the tie line plate point in this, that type of type 2 system, or we will be discussing this one in detail about that, the conversion of type 2 system into type 1 system. So we will be discussing in detail also on that. Now we will be this one drawing this right angle triangular diagram from the, we can say this one ternary diagram. So let us take, say we have drawn this, we can say a small part of this ternary diagram, just we have not mentioned the C part actually, this where the C 100% C is present, that part, because you see in the extraction process also we will see that this 100% C cannot be this one separated using this one. So that part actually is not so important. So we will be discussing this part where the equilibrium is, means binary phase zone is there. Suppose here actually this binary phase is there, we told that these binary phases are like this, where the, we can say this one C is miscible in any proportions into both A and B, or we can say the carrier solvent and the extracting solvent, which has this plate point. Like this, the mass fractions of the solute in two phases like this in the raffinate and extract at equilibrium are plotted against the corresponding mass fraction of the solvent. So that is we will be drawing also from this, we can say this one right angle triangular diagram, we will be able to get the, say we can say this one equilibrium values of this XC and YC. How we will be drawing this one, we are discussing in detail like this. So concentration of the extract phase are, suppose this one up to this, we can say this one. So that will be, say from Q point to P point, we can say this one will be XP versus XC. That is why that is XP versus XC. And after that point P to R, it is actually, we can say this one YB versus YC, that is YB versus YC is there. But whenever we will be drawing one tie line, you see this, all these are actually drawn from the tie line data. Suppose this P has this, we can say this one P will be lying for in the, say diagonal of this XC and YC, because you see the P is the common point, where we can say this one, here you see the in plate point XC is equal to yc. That is why we say this one is the tie line, the plate point. So, this is corresponding to plate point, this plate point. And whenever we will be drawing any tie line, suppose this is the one tie line. So, from here what we will be doing, this is corresponding to, we can say this one, this xc and yc also. Suppose this is yc and this is xc. Okay. So, that is why whenever we will be coming to this point, that is we can say this one, this is yc, this one is yc, and corresponding value, this one is called this, corresponding value actually is called this xc, this is xc. So, whenever the equivalent to xc, whatever the yc value is there, from this tie line we will be able to get this one. So, we have this xc and we have this yc, this is one cutting point. Let us take this tie line, here also you see this one is xc value, we will be coming to this diagonal line, and corresponding this actually is yc value. Means say how we will be getting this one, we will be extending this xc and up to yc value, then whenever it will be meeting one point. So, that way for all the tie line values we will be getting these common points. For any xc value, suppose this another yc value is there. So, using this one we will be getting the common points like this way. So, then we will be able to get the, say we can say this one equilibrium line, and whenever we will be joining this equilibrium line, we will be getting that the corresponding to xc value, what will be the yc value. Okay. And we will be frequently we will be drawing this equilibrium curve for the extraction calculation, and say we can say this one for the extract phase, in all the cases we will be denoting ya, yb and yc, and those are the raffinate phase we will be taking this one, the xa, xb and xc. So, these are the common notations actually we will be using for the entire extraction calculation. Then the raffinate arm PQ is obtained by plotting the points like this xb and xc. Suppose this raffinate arm will be getting this one by plotting this xb and xc, and extract arm will be getting from this plate point by plotting this yb versus yc. So, we will be getting this one. So, raffinate arm will be getting by plotting the set of yb and versus yc. Okay. So, here also this P is the plate point, and point D1 actually on the raffinate arm and D2 on the extract arm represent the composition at the equilibrium. That we told that, say whenever we have this D1 and D2, say from D1 we can say this one nothing but this is the xc value. So, this is we can say this one corresponding to xc, and so whenever this we have this xc, we will extend this one, and from here you see this one yc will be getting, suppose this is yc value, whenever it will be cutting, so it will touch this line. So, D1, D2 that is the tie line. So, all the tie line values actually all the tie line data points are there, and from there we will be able to get the, we can say this one equilibrium line. Okay. Also equilibrium diagram can also be drawn on the xc yc plane also, that also we can say this one we will be discussing this one. So, means this one or this one anything will be okay for this one what is called general calculation. And in another way also, that is also very convenient method of this equilibrium plot on the solvent free basis. Like this, in this presentation of this liquid equilibrium data, the mass ratio of the solute we can say this one in x and y in two phases, like this we can say this one are plotted like this. We can say this for capital X, we can say this one capital L X and small z will be in the raffinate phase, and capital Y and capital Z in the extract phase. Will be used this one. So, that is we can say this one all the values are in the solvent free basis. We will be discussing the advantages of the solvent free basis calculation also. So, the quantities capital X, capital Y, small z and capital Z are defined like this. So, we need to remember this one, capital X is equal to small x c by small x a plus small x c, and where the small z is equal to small x b by small x a plus small x c. Whereas, this y that is in the we can say this one extract composition, that is equal to y c by y a plus y c, where capital Z, that is we can say this one y b by y a plus y c. So, this capital X and small z, that we can say this one, that is in the raffinate phase composition, and in extract phase, that is capital Y capital Z. So, we will be calculating this one, we will be solving one small problem to understand that whenever we will be drawing this equilibrium plot on the solvent free basis, and from there actually we can see all the calculations are very simple. This diagram, that is we can see this in the equilibrium plot of the we can say this extract arm and in the raffinate arm is called this Janicki plot, or we can say this one Meloni-Savart diagram also, or we can say this one Janicki diagram. So, it is very convenient way of this one calculation for the extraction process. Like say we will be solving one problem, very simple problem actually, how to plot this one, and from there we will be able to know that how this we can say this one equilibrium plot is done on the solvent free basis. The problem is that draw the Janicki diagram for a liquid system using the following equilibrium data. Also show the tie line in the diagram. Like this, in the raffinate phase, say we have this x a is equal to suppose 0.939, where is the x p is equal to 0.0601, where x c is equal to 0. So, in one point, that is we can say that in the left hand corner, where we can say this only the extracting solvent and we can say carrier solvent is there, there is no solute like this, and say this one x a is going on decreasing slowly, and somewhere we can say this one no extracting solvent is present, where this x b is there and x c value means we can say the solute contribution is maximum in the raffinate arm, where 0.8897% is there. So, if we add all this, we will be getting 1. And for extract phase, so we have this one, we can say whenever this 0.06 y a is there, and say we can say this y b is maximum 0.94. So, and say like this is the right hand corner actually, and we can say this one y c actually there also is 0. So, whenever we will be plotting this one in the raffinate arm and extract arm, we will be getting one common point, like this we will be getting this plate point also. So, we will be coming to that point, this plate point also will be getting, but we will be doing this one in the Janicki diagram, means we will be plotting this one in the solvent free basis. Okay. So, for that we need to calculate these 4 parameters, like this capital X, small z, capital Y, capital Z. So, these 4 will be calculating, then we will be plotting this raffinate arm and extract arm in the, so we can say this one solvent free basis in the equilibrium plot. Okay. So, now we will be calculating this one for this all these data points, we will be calculating those, like this what we will be doing for this suppose for first data point like this for the raffinate arm, we have x is equal to 0.3939, x b is equal to 0.0601 and x c is equal to 0. So, we can say this one as this x value is equal to x c by x a plus x c. So, will be 0 by 0.939. So, it will be 0 like this. Okay. For second this one data point 0.73, this one what is called for x c is equal to 0.0219 divided by 0.7327 plus 0.0219. So, it will be coming as we can say 0.0239. For the third one, like this 0.4866 divided by 0.4404 plus 0.4866, it will be like this 0.525. And for the next point, like this 0.664, so it will be like this 0.73. And for 0.7923, we will be getting this one 0.885. And for 0.8897, we will be getting this one as 0.8897 by 0.8897, that is we can see this one we will be getting x equal to 1. For z calculation also we will be following the same x b divided by x a plus x c. Suppose for first point 0.0601 divided by 0.7327 plus 0.0219. So, we will be getting as like 0.064. For other point actually, for the next point we will be getting 0.067. For next point actually we will be getting 0.079. This next point will be 0.099. Then it will be 0.117 and then 0.124. For capital Y, that is we can say this one for extract arm. So, these 2 points are this one for raffinate arm. So, we will be drawing this one in xy versus zz plot. Actually this all the values are, we can say this one, whenever x will vary from 0 to 1, you see small z values are all within, we can say this one 0.124, means that is almost, we can say this one will be in the line of this zz this one axis, means we can say it will almost along the xy line. Okay. And for extract arm actually, so we can say these two this one points will be for raffinate arm. Now, extract arm actually we will be calculating like y is equal to y c by y a plus y c, like this y c is equal to 0. So, definitely this first point will be 0. Then we have this for second point we have this y c value is 0.03 divided by 0.052 plus 0.03, that is we can say we will be getting this 0.366. And the third point will be like this. For third point we have this 0.084 divided by 0.036 plus 0.084. So, that will be coming as 0.7 and the next point will be 0.876 and then the next point will be 0.96 and the last point will be this one y c is equal to 0.17 this one 54 divided by 0.1754 as y a is equal to 0. So, then it will be like this 1. Okay. Corresponding to capital Z value, that is we will be starting with this middle values of like this y b. So, it will be work like 0.94 divided by 0.06. So, 0.94 divided by 0.06, it is coming as 15.67. Then second value will be 0.918 divided by 0.052 plus 0.03, that is coming out as 11.2. Okay. For the third value 0.88 divided by 0.036 plus 0.084. So, it is coming out as 7.33. The next value will be like this. In the same way, we will be calculating 0.851 divided by 0.0185 plus 0.1305. So, it is calculated as 5.71. Then the fifth value is calculated as 0.8276 divided by 0.0069 plus 0.1655, that is calculated as 4.8, and for 0.8246 divided by 0.1754, it is coming out as 4.7. So, now these 2 points are for extract arm. So, now we will be plotting these all these in the we can say this one x y versus z z plot. So, for first we can say this one, whenever we have this x is equal to 0. So, this z is equal to small z is will be like here. So, this is first point. Then 0.0 to 0.0239. So, it will be like here also, somewhere here 0.067, here also somewhere it will be like this. Then so then we have 0.525. So, here actually it will be like this, for that 0.079. So, 0.525 means somewhere here. So, it will be like this 0.079, 0.73 somewhere here it is for 0.099. So, it will be like this. So, just below 1 like this, 0.1 actually say here somewhere, and then this 0.885 like this somewhere, 0.885 here, it is for 0.117 somewhere here, and for 1 it is 0.124 like this. So, somewhere here. So, if we plot this one, it is like touching this, we can say this xy axis like this. So, this is, we can say this one, this raffinate arm. So, this is raffinate arm. For extract arm, we can say this one will be getting for y is equal to 0. So, this one is y is equal to 0. So, it is around 15.67 like this, it is somewhere here. For y is equal to 0.366. So, somewhere here. So, we will have this one for 0.366 like this, it is 11.2. So, it is like this somewhere here. So, it is 11.2 like this. So, this we have. So, for this second one, for 0.7 it is 7.33. So, it will be like this for 0.7, that is 7.33, 7.33 like here. For 0.876 like this, for 0.876 it will be like this 5.71, around 6 here. So, it will be like this, and for 0.96, so it is 4.8, 4.96 means here it is 4.8, around 5 here, and for 1 it is 4.7. So, it will be like this, it is here somewhere. Now, you see this one, we have this all this line, if we draw, add all this or join all this. So, we will be getting this one as the extract arm. Now, we need to draw this, we can say tie line. So, this one tie line, that is we can say this one, this first point actually. So, this is one tie line, we can say this one. So, this one, the second one actually you see, this is second tie line, then we have this third tie line, then fourth tie line, then fifth tie line, this is the sixth tie line. So, all these are, we can say this one, all these are tie lines. So, we can say this one, say raffinate arm is nothing but we can say capital X versus small z, and extract arm is equal to capital Y versus capital Z, and these are all we can say this one, say tie lines. So, this is tie line, we can say this one, this is tie line, this is also one tie line, we can say this one, this is another tie line. So, this is one tie line, this is one, and this is also one tie line. So, now we have this one, the extract arm and raffinate arm. Now, actually we can say using this solvent free basis equilibrium diagram, we will be able to calculate the entire extraction calculation also using this Janicki diagram. So, this is we can see this one Janicki diagram. Okay. So, thank you. This in the next class actually we will be discussing about the effect of temperature on the liquid equilibria.